In the last class, we have discussed about Fleming's left-hand rule, and today we will discuss about the application of Fleming's left-hand rule. So let us start electric motor. First of all, we will have to know what is electric motor. Electric motor is basically a device that converts electrical energy into mechanical energy. An electric motor is based on the principle that when a current carrying coil placed in an external electric field, then the coil experiences couple of force which is equal and opposite in magnitude. So दो बच्चे वेट कर रहे हैं. Just let me see. Yes. Now, okay. So before going deep into that, first of all, we have to learn about the magnetic force acting on current carrying conductor that I have discussed in the last class. So magnetic force F that act on the conductor which carries current when placed in external magnetic field experiences a force which is equal to the product of length of the conductor within the magnetic field and current flowing through the conductor and magnitude of external magnetic field B, as well as the sine of angle between the conductor and magnetic field. So mathematically, once again recap it, because this formula will be used while describing electric motor. You know well that when current carrying conductor placed in an external magnetic field, the conductor experiences a magnetic force, and this force is just equal to product of length of the conductor within the magnetic field and current flowing through the conductor and external magnetic field B, as well as the sine of angle between the conductor. So in short, the magnetic force will be just equal to magnitude of product of magnitude of magnetic field, amount of current flowing through the conductor, and length of the conductor lying in the magnetic field, and sine of angle between the current and magnetic field. So you see here that if angle between current and magnetic field is 0, then force becomes 0. And angle between current I and magnetic field B is 90 degree, then force becomes maximum because sine 90 equal to 1. So force becomes maximum, and maximum force will be just equal to ILB or BIL because sine 90 equal to 1. So maximum force will be this much, and next one is, so this is the expression for the force, magnetic force acting on a current carrying conductor when placed in external magnetic field with field strength B and length of conductor lying in this field. Then magnetic field is just expressed as F equal to ILB sine theta. It means magnetic force depends on orientation of current carrying conductor with respect to magnetic field. So now keeping in mind this formula, magnetic force F equal to ILB sine theta, then we will able to describe uh, electric motor. Now try to understand the force on current carrying conductor when placed in an external magnetic field B. Try to understand here, when a current carrying conductor is placed in an external magnetic field, there is an interaction between the magnetic field produced by the current in the conductor and permanent magnetic field. You see, now try to understand, as we place current carrying conductor in external magnetic field in terms of permanent magnet, and there is an electromagnet. That is, electromagnet is due to current flowing through the conductor. So the two magnetic field interact with each other. That's why the current carrying conductor experience a force, and this leads to a force being experienced by the conductor. Okay. Now you see here, this is the current carrying conductor in which current flows in this way, and this is the magnetic field. You can say that there are two magnets placed, north pole of the magnet this side and south pole of the magnet this side. Then magnetic field line will move in this way. Therefore, angle between the current and magnetic field is 90 degree. Therefore, this conductor would experience maximum force F max, which is equal to ILB, because sine 90 equal to 1. But in this situation, you see here current and magnetic field both are parallel to each other. Therefore, angle between the current and magnetic field is 0. So sine 0 equal to 0. Therefore, ILB sine theta, F equal to ILB sine theta equal to 0, because sine 0 equal to 0. Therefore, force is 0. So when current carrying conductor is placed in parallel to the magnetic field, then no force is experienced by the conductor. But when it is placed perpendicular to the magnetic field, then it experiences maximum force. And this concept will be used. Keep in mind. Now, in the last class, we have discussed that so far we have discussed that current carrying conductor when placed in external magnetic field experience magnetic force. Now, question is that how to determine the direction of magnetic force acting on current carrying conductor. Direction is determined using Fleming's left hand rule. In the last class, we have discussed what is Fleming's left hand rule. If one stretch forefinger, middle finger, and thumb of left hand in such a way that forefinger pointed in the direction of magnetic field and middle finger pointed in the direction of current, then thumb will give the direction of force. So here it is thrust, you must say force. So look at here. You place your middle finger along this length like this, and your forefinger in this direction. Then your thumb will be in this direction. That is, your thumb will give the direction of force acting on the current carrying conductor. It means this conductor would experience a force in this direction. If direction of current is reversed, then direction of force also gets reversed. or if direction of magnetic field is reversed, then direction of force also get reversed. Now, okay, so you have got it. And now this one is the directional relationship of current in the conductor and the external magnetic field B and the force the conductor experiences. Remember here directional relationship. Here right now this is north pole and this is south pole of the horseshoe magnet, and magnetic field right now is from north to south here, that is indicated by the arrow. So this is the magnetic field B in this direction, and current in this conductor is in this direction I. Now we have to decide force. So just place your forefinger of your left hand in downward in the direction of arrow here, and then middle finger of your left hand in this direction. Then your thumb will indicate the force outwards. That means this conductor will experience a force outwards. That means this conductor will get displaced outwards in this way. Now, if direction of current reverse in this conductor, then direction of force also get reversed. That will be inwards. Now, if direction of current is not reversed, instead we reverse the direction of magnetic field. That is, place the north pole on the bottom sides and south pole on the top side, then force get reversed. So direction of force acting on a current carrying conductor will depend on two factors, on direction of current and on direction of magnetic field. If both the direction of both current and magnetic field is reversed, then direction of force will remain unchanged. If direction of one of them is reversed, then direction of force would also get reversed. So this was the things. Now come to the points. How electric motor works. You see here, this is the south pole of a magnet and this is north pole of a magnet. So these two poles will generate a magnetic field in between this region. So for this coil, rectangular coil, this region will be treated as external magnetic field, a region of external magnetic field. Magnetic field will be directed from this pole to this pole, that is in this direction. And you see here, battery is connected. So this is positive terminal and this is negative terminal. So if current starts flowing in this way, and this is a carbon brush and this is a splitted ring, there will be two splitted ring, commutator ring, and two carbon brush. Carbon brush just make in contact with the ring and coil is attached with the ring. So ring keeps rotating as coil rotates, but electrical contact is being maintained with this carbon brush. So electrical supply is from external circuit to this coil is made through this contact, carbon brush and commutator ring. So as current passes through this coil, this is the longer arm, this is the longer arm, and this is the shorter arm, width of the rectangular coil. So no magnetic force act on this arm because magnetic field is in this direction and current in this direction. Current is in this direction, so you can say that magnetic field and current in this arm makes an angle of 180 degree and sine 180 degree equal to 0. Similarly, magnetic field in this arm electric current in this arm in this direction, but magnetic field is in this direction. So angle between magnetic field and current in this arm is zero. So again, magnetic force acting on this arm and this arm is zero. Now we have to check the magnetic force acting on the longer arm. So you see here direction of current in this way. So here current is flowing in this arm in this way. A magnetic field is in this direction. So put your forefinger of left hand in this direction and your middle finger in this direction. Then you will see that your thumb will be pointed upwards. That means this arm will experience a force which will be directed upwards. That's okay. And direct magnitude of force will be just equal to ILB sine 90 degrees. Therefore, sine 90 degree equal to 1. So force will be ILB and upwards. Now come to the point on this arm. We have to calculate magnetic force acting on this arm. Again, force acting on this arm will be ILB sine 90 degree. Only difference is that in this arm current is in this direction and in this arm current is in this direction. So in this case current is in this direction. So place your middle finger along this direction and your forefinger in this direction, that is from north to south. Then you will see that your thumb will be pointed downwards, indicating that magnetic force acting on this arm in downwards. But magnitude of this force is also ILB, and here magnitude is also ILB. Only difference is that in this arm force is acting upwards and force is acting in this arm in downwards. So two force acting on two arm and line of action of force is different. That's why the coil would tends to rotate about the axis. That is not shown here, but I say you this is the axis passing through the mid of the coil and ring. So this rotation of the coil means rotational kinetic energy is nothing but mechanical energy. Here we supply electrical energy through this coil, and in turn coil starts rotating, so we get mechanical energy, and that mechanical energy can be used for various purposes, for floor grinding machine and for electric motor to draw water from the ground, and for various purposes this mechanical energy can be used. And this is the parts of electric motor. That was the brief discussion about for electric motor. Most essential requirement is that you must have a strong field magnet, that is you must have permanent magnet that must be strong, and here north pole of one magnet is placed this side and south pole of one magnet is placed this side. So in between the space between north pole and south pole there will be a magnetic field of uniform magnetic field, and in this region between the two poles we place a current carrying rectangular coil. So coil starts rotating because of couple of force, and that's why this coil will have rotational kinetic energy that can be used as a mechanical energy for various purpose. This is the commutating ring, commutator, which is made up of metals and is fixed with the ends of the coil, and as coil rotates this ring also rotates. So during rotation electrical contact must be maintained. So this is done with the help of carbon brush. Here there are two carbon brush. So one carbon brush is connected with the positive terminal of the battery and other carbon brush is connected with the negative terminal of the battery. So just you have to now move on. When this coil after rotating comes to the vertical position, you see here, when this coil comes to the vertical position here, again magnetic force acting on this arm and magnetic force acting on this arm. Try to understand. Right now current in this arm is in this direction while magnetic field is in this direction. In this case, magnetic force experienced by this arm is non-zero because angle between the current and magnetic field is 90 degree. Therefore, magnetic force on this arm is non-zero. Now try to understand. In this case, magnetic force acting on this arm, place your middle finger along this length and your forefinger in the direction from north to south. Then you will see that your thumb will be pointed outwards in this direction. In this direction. So it means this arm will experience a force in this direction, outwards, in this position. And in this case, this arm would experience a force in this direction. So these two forces are equal in magnitude but opposite in direction. So this will cancel out each other because the line of action of force are same. So if equal and opposite force act along the same line, then their vector sum will be 0 and their turning effect is also 0. That means no turning or rotational effect will be there. So due to these two forces acting on this arm, width of the rectangular coil, no turning effect is there. Now come to the point on the longer arm. So current is flowing in this way, anti-clockwise. So here current is in this direction. So a magnetic field is in this direction. So maximum force will experience by the longer arm, but direction of force will be upwards here. You see, in this direction, upwards. And now come to the point. Here current is along this direction. So you just place middle finger along this length and forefinger from north to south. Then your thumb will be pointed downwards. So again, these two forces are collinear. Therefore, their rotational effect is 0. Their rotational effect is 0 and their vector sum is also 0. So in vertical position, net turning effect on the coil is 0, but due to inertia, because from the horizontal position to vertical position it acquires some motion. So due to inertia, it keeps on moving, rotating, and again as soon as its vertical position changes, again net turning effect comes into play, and so there is a continuous turning taking place in the coil, and hence continuous mechanical energy is produced by supply of continuous supply of electrical energy. So that was the brief theoretical description or explanation of electric motor. Now try to understand. An electric motor is the basis of an electric motor. An electromagnet is the basis of an electric motor. Without electromagnet, one cannot have electric motor. Say, if you have only permanent magnet and no electromagnet, that is no current supplied through the coil, you would not get turning effect and hence your electric motor would not work. So basic concept behind that one is electromagnet. That means there must be one permanent magnet and there must be electromagnet. Permanent magnet cannot be increased or decreased as per desire, but electromagnet can be increased or decreased as per desire by supply of current. So, an electric motor is all about magnets and magnetism. So, electric motor is based on all about magnet and magnetism. A motor uses magnets to create motion. And best example of electric motors in your house right now, you are in your room and there must be electric fan there in that room, hanging with the roof of your house or your room. So electric fan is nothing but what? Electric motor. This is the common example of electric motor. Now, opposite poles attract and like poles repel. That things has already been discussed. Inside an electric motor, this attracting and repelling force creates rotational motion. And hence, motor is consist of two magnets. That magnet is called field magnets. After that, we have to discuss about parts of motor. We say first part is armature, that is frame over which uh, a coil is wrapped, that is called armature. You see here, I just come to the here. You just this is the virtual diagram of the coil, but a copper wire cannot be so strong to withstand the magnetic force acting on this arm, so it will get deformed. So to prevent the deformation of the coil under action of magnetic force, we wrap the coil over the solid strong frame, that is called armature, and this frame is capable of rotating about an axis, and that's why as soon as the current passes through the coil, the magnetic force shifted over the armature and armature keeps on rotating. That's why mechanical energy is produced. Here you see, so armature is the solid and a strong frame over which a coil is rotated, and this frame is capable of rotating about fixed axis. And next part is commutator. In case of DC motor, this is a semicircular ring, a splitted ring called commutator, because during rotation these two rings commutes with the external supply of the electric current, and this commutator is being in contact with the carbon brush, because you know that carbon brush is nothing but what? Graphite rod, and you know that graphite is slippery in touch. That's why uh, less friction is there between in contact between the commutator and graphite. And so but graphite is also good conductor of electricity, so being in contact with the commutator keeps continuous electrical contact with the commutator and supply electrical energy to the coil, that is converted into mechanical energy. And next one is axle. Axle, it passes exactly in the midway of the frame or the coil. And next one is field magnet. This is the permanent strong field magnet placed in terms of bar magnet here. This is called field magnet. This is called field magnet. So field magnet, and then after arranging all these four parts, 5 parts together, then we get electric motor. And we supply DC power to such arrangement, then this electric motor is called DC motor. But for AC motor, we have to change commutator, and everything will remain same. Only commutator has to be changed. In AC motor, commutator must not be a splitted half ring, but it will be a complete ring, and there will be two complete ring used in that. In case of DC motor, we take only single ring, that is a splitted half ring, and making two half ring a single ring. So once again look over the figure. If you have electric motor in this shape, this is the commutator ring. So this is a splitted ring, half ring and half ring. Then this must be DC motor. So you have to supply DC electric current. You have to supply DC power supply. You have to connect the circuit with DC power supply. But in case of AC, everything arrangement will remain same. Only you have to replace this ring, and in place of it, you take two complete ring, not a splitted ring, but you take two complete ring and arrange them. Connect one complete ring with one terminal and other complete ring with another terminal of the coil. Then this becomes AC motor. Only difference is that only changing the commutating ring, electric motor converted into AC to DC. Now this is the illustration you see here. This is the commutator ring, and this is the north pole magnet, and this is the south pole magnet, and this is the armature, a solid armature over which copper, insulated copper wire is wrapped, and here DC supply, battery connected with the terminals. So as soon as current passes through this coil, due to this magnetic field, permanent magnet, and this in this coil electromagnet, it starts rotating, because you know that this terminal will act as south pole, so south pole get attracted towards this north pole, and this terminal act as north pole, so it get attracted towards this south pole, and so on. So keep on rotating. Okay, now try to understand what is armature. In order to understand armature, armature is an electromagnet made by coiling thin wire around two or more poles of the metal. The armature has an axle, and commutator is attached to the axle. When you run electricity into, when you pass electricity into this electromagnet, it creates a magnetic field in the armature, and that attracts and repel the magnets in the stator, so the armature spins through 180 degree and hence converted into mechanical energy. To keep it spinning continuously, you have to change the poles of the electromagnet. So for changing poles of electromagnet, commutator is simply connected, and basic purpose of commutator is to change the poles of electromagnet. So commutator is simply a pair of plates attached to the axle, pair of plates, or you can say rings. These plates provide the two connection for the coil of the electromagnet. Commutator and brushes works together to let current flow into the electromagnet and also to flip the direction that the electrons are flowing at just the right moment. So it changed the direction. So change the direction of poles. Now the contact of the commutator are attached to the axle of the electromagnet, so they spin with the magnet. Brushes are just two pieces of the springy metal or carbon brush or graphite that makes contact with the contact of the commutator. And now a spinning armature. Remember, you see here, this is the spinning armature. Spin about this one. And here real picture of electric motor is that this is the coil, this is the coil, this is the coil, and this is the coil. So this is actual picture of motor and this is the axle. Your electric fan is arranged in this way. So when current is supplied to this coil, and this is the magnet, you see here, this is the magnet. Here outside a magnet is placed there. So as soon as here a magnet is placed, here a magnet is placed. So then this coil, when current passes through this coil, this acts as north pole or south pole depending on the direction of current through the coil. And here you place, if north pole, then this north pole and this north pole will repel each other. So it will continue, it will rotate, move away from this north pole. So here north pole has not given here. You can say that there will be a cap over this arrangement. So in that cap, the similar thing, just like this is the convex, then here will be concave shaped magnet will be arranged, and that concave shaped magnet will act opposite to this one. That's why they will repel or attract each other, hence rotation will be created. And here ball bearing is arranged here. So during rotation less friction is produced. So maximum electrical energy converted into mechanical energy. So this is the real picture of electric motor. Now on basis of that lecture, you can answer these questions. A current carrying coil in a magnetic field experience a turning effect. Variable power supplied. Then now how can the turning effect be increased? One question. How can turning effect be increased? Option 1. By increasing the number of turns on the coil, or reducing the size of current or amount of current through the coil, or reversing the direction of the magnetic field, or use the thinner wire of the coil. Which option you will go? That you have to think over this one. Which option you will go? You have to increase the turning effect. So think, keeps on thinking and try to answer this question. And in the next class, I will ask you, what are the direction of force on the left and right loop here? Here you have to determine direction of force acting on left and right loop. Applying Fleming's left hand rule. Again, a student sets up the apparatus shown in the order to make a relay. You see here. Now, which metal would you use to make the core? So, core must be of which metal? Today, I will not say you, but you must keep thinking and then try to answer. Hello?
हेलो
हाँ जी बोलो.
सर ये नहीं समझे
कौन सा?
ये सर जो क्वेश्चन है
अभी वाला.
सर इसको यूट्यूब पर कीजिएगा.
हाँ यूट्यूब पर तो सभी ये सभी जाएगा, ये सभी को हम यूट्यूब पर भेजेंगे. ठीक है.
ठीक है सर.
और इसलिए इस पर सोचना है और आंसर देना है, और फिर मैं नेक्स्ट क्लास में अगर दिक्कत होगा तो एक्सप्लेन करूँगा। ओके, नाउ आई थिंक दैट this is all about the motors. Now we have to one more thing that you have to.
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, in elementary model. One single turn of conductor is placed between two opposite poles. If we start to supply DC, via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and right side conductor, then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because turn, conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, by due to moment of inertia, turn continue to rotates and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force, with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is aligned in direction of magnetic field, that is, from north pole to south pole, and second finger is aligned in direction of a current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is aligned in direction of magnetic field, that is, from north pole to south pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, turn, tends to rotate in clockwise direction. From that explanation we can come to conclusion that here in this model we can see that whichever conductor comes near South Pole, experience upward mechanical force, and near North Pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil. And instead of 2 poles there is number of poles, installed. I hope that you like it.